This topic is important as we look from the gate point of view, and this topic is also important for understanding the signals and systems properly. Okay, if we say a Laplace transform, what does it mean? What is the definition of Laplace transform? Why it is required? What is the importance of it in signal processing? This topic is also there in mathematics. Then what is the difference between the Laplace transform in mathematics and Laplace transform in signals and systems? Basically, there is no big difference between them, but only when it looks for the signal analysis, we call it Laplace transform. We use Laplace transform in signals and systems. Otherwise, if we are using Laplace transform for the function, then it goes to mathematics. Okay, simple. Now, the formula for Laplace transform is Fs is equal to minus infinity to infinity ft e to the power minus st dt. E to the power minus st is called kernel function. E to the power minus st is a function which is solely required to find the Laplace transform. We'll see there is a lot of similarity between this e to the power minus st and e to the power minus j omega t. We'll compare this with Fourier transform. Now, what is this S? We have to see the importance of this S. S is equal to sigma plus j omega. In a two-dimensional plane, I can write it like this. This is my j omega and this is my sigma. Sigma minus j omega. This whole plane is called S plane. So whenever I am finding my Laplace transform, I am finding it on the S plane. I am finding it on the full plane. But whenever I am finding the Fourier transform, I am finding it on the j omega axis only, not on the S plane. So that is a basic difference which lies between Fourier transform and Laplace transform. We'll see. We can also say that Laplace transform is a general case and Fourier transform is a special case of Laplace transform. It will become more clear when we will study the Fourier transform. But presently, we should remember the basic formula for the Laplace transform. Now we will find the Laplace transform of few general functions or few general signals of time. Okay. First one. signal xt equal to ut. Ut is a unit step access is equal to minus infinity to infinity ut e to the power minus st dt. It will become 0 to infinity 1 dot e to the power minus st dt. On solving this, we will get access equal to 1 upon s. Similarly, second one, xt equal to tut. Access, it can be found by a similar method, again minus infinity to infinity tut e to the power minus st dt. Solving this integral, I'll get 1 upon s square. Xt equal to e to the power at ut. Then x is equals to minus infinity to infinity e to the power at ut e to the power minus st dt. This is equal to 1 upon s minus a. Okay. Next will be xt equals to t dot e to the power at ut. Then xs is equal to integral of minus infinity to infinity t dot e to the power at ut dot e to the power minus st dt. Become 0 to infinity t dot e to the power at e to the power minus st dt. Xs equal to 1 upon s minus a whole square. In general, if we want to find xt equal to t to the power n dot e to the power at ut, xx is equal to n factorial upon s minus a n plus 1. This can be found in the similar way by solving the integral. Okay, next. If xt is equal to sine omega naught t ut, then to find xs, we can write it like this: minus infinity to infinity sine omega naught t ut e to the power minus st dt. Now this can be written as 0 to infinity sine omega naught t e to the power minus st dt. Sine omega naught t can be written as e to the power minus j omega naught t minus e to the power minus j omega naught t upon 2j. Substitute 1 in the above equation of excess, then excess can be written as 0 to infinity e to the power plus j omega naught t minus e to the power minus j omega naught t upon 2j dot e to the power minus st dt. Now use Laplace transform of e to the power at ut to get excess. Excess is equal to omega naught upon s square plus omega naught square. Similarly, for xt equal to cos omega naught t ut, excess is equal to s upon s square plus omega naught square. This is left as an exercise to the student. Next, xt equal to e to the power minus at sin omega naught t ut. For finding the Laplace transform of this, again it is more or less similar to finding the Laplace transform of sin omega naught t and e to the power at ut. Finally, the Laplace transform which is going to come in this case is omega naught upon s plus a whole square plus omega naught square. The formula is again the same formula, x is equal to 0 to infinity e to the power minus at e to the power plus j omega naught t minus e to the power minus j omega naught t upon 2j multiplied by e to the power minus st dt. Solve this to get excess. So these were the few general Laplace transform for few important signals. Now coming to the very important topic which is called region of convergence. What is the importance of region of convergence? To just say that region of convergence is the only property which is not defined in Laplace transform when we use it in mathematics. But when we use Laplace transform in signals and systems, we use to define the region of convergence also. Okay, to understand what is the region of convergence. See, we have seen that excess is equal to minus infinity to infinity xt e to the power minus st dt. Okay, substitute s equal to sigma plus j omega. Let this equation be 1. We get excess equal to minus infinity to infinity xt e to the power minus sigma plus j omega t dt. Okay. Now I can separate the term and can write it like this. So we can see from this equation that e to the power minus j omega t oscillatory function and e to the power minus sigma t is either damping or converging or diverging factor. That means e to the power minus sigma t tends to infinity if sigma is lesser than 0 and t greater than 0. E to the power minus sigma t tends to 0 if sigma is greater than 0 and t greater than 0. That means depending on the value of sigma, it can be either converging or diverging. Now, looking from the signals and system point of view or from signal analysis point of view, every function xt should be of finite. That means energy present in the system should be finite. Or when we integrate that system, when we integrate that function from minus infinity to infinity, the value of the function should be finite. Value of the integral should be finite. Now, if I give e to the power minus sigma t, where sigma is lesser than 0 for t greater than 0, then my integral minus infinity to infinity xt e to the power minus sigma t dt tends to infinity. So when it tends to infinity, that means it is not converging, it is diverging. So I have to take the values of sigma for which my given function xt converges. That means that is the reason this is called region of convergence. The region of convergence are those values of sigma or the real part of function s which converges the function xt. Now we'll see the importance of region of convergence. To understand the importance, just we'll consider a function xt equal to e to the power minus at ut. Xs equals to 1 upon s plus a. Okay. Xs I can write it also like this, minus infinity to infinity e to the power minus at ut e to the power minus st dt. Now again separating the real part and imaginary part of s and merging it with e to the power minus at, I will get 0 to infinity e to the power minus at e to the power minus sigma t e to the power minus j omega t dt. I can write it like this, 0 to infinity e to the power minus sigma plus a t e to the power minus j omega t dt. Now for integral 0 to infinity e to the power minus sigma plus a t dt to be converging, sigma, we have to define the value of sigma for which this function is converging. Okay, by looking at this e to the power minus sigma plus a t dt, we can say that sigma value should be greater than minus a for this to converge. If I plot it in a S-plane, then minus a is here, region of convergence is this. Means my ROC is real part of S should be greater than minus a. It cannot be equal to minus a because at point equal to minus a, it will become 1. When it will become 1, again the integral is going to be infinity. That means ROC does not contain the point itself but all the values other than that point. Now we will see Laplace transform of another function which is equal to minus e to the power minus at u of minus t. Again, excess for this is written as minus infinity to infinity minus e to the power minus at u of minus t e to the power minus st dt. This I can write it as minus infinity to 0 minus e to the power minus at e to the power minus st dt. This is again equal to 1 upon s plus a. Looking from the previous one, the Laplace transform of xt in the previous case and Laplace transform of xt in this case both are same. That means Laplace transform is same. Then how to differentiate between these two? They can be differentiated on the basis of region of convergence. Now looking for the region of convergence in this case, we have xs equal to minus infinity to 0 e to the power minus a plus sigma t e to the power minus j omega t dt. Now for integral minus infinity to 0 e to the power minus a plus sigma t dt to converge, we must have sigma lesser than minus a. Plotting it on the S plane, I will have minus a point here, all the region, the left hand side of this is my ROC. Real part of S should be less than minus a. So two different signals having the same Laplace transform can be differentiated on the basis of their region of convergence, not on finding the Laplace transform only. So that is the basic difference when we talk about Laplace transform in signals and systems and Laplace transform in mathematics. So we have seen the following important things. Note first. First one is imaginary part will never contribute for ROC. Real part will only contribute for ROC. ROC is always unique. That means there can be two different signals having the same Laplace transform but different region of convergence. We have seen earlier in the previous case there are two signals, xt equals to e to the power minus at ut. I'll call it as x1t. x2t equals to minus e to the power minus at u of minus t. x1s Laplace transform of x1t is again 1 upon s plus a. x2s is again 1 upon s plus a. But ROC in the previous case is real part of s greater than minus a. ROC in the second case is real part of s lesser than minus a. Second, fourth point. ROC does not include the point at which functions become 1. That means ROC in the previous case, if we see that ROC will never include poles, minus A is not included in region of convergence. Fifth point regarding the nodes in the ROCs. ROCs always contains the line parallel to j omega axis. That means they will always contain line parallel to j omega. For finite duration signal, which is absolutely integrable. For them, ROC is entire S-plane. Okay. So these are the few properties for region of convergence. Okay. Next topic in this will be regarding the properties of the Laplace transform. Okay, there are several properties of the Laplace transform. Just general properties like okay, before starting we'll just like to say something about the properties of this. The properties like linearity, time shifting, shifting in S domain will be helpful for finding the Laplace transform. How means if we know the basic Laplace transform of the few signals, the signals which we have for which we have found the Laplace transform earlier, and if we know the properties, then we need not to find the Laplace transform using the basic formula of Laplace transform. Directly we can apply the properties and directly we can find the Laplace transform. Now the effect of the effect of mixing, effect of time shifting, effect of time scaling will also be there in the ROC of the Laplace transform. Okay, so when we consider the when we do any operation on the signal, on time or on amplitude, then there will be an effect on the ROC also. We have to take care of that effect of ROC while finding the Laplace transform. Okay, we'll start with the properties of the Laplace transform. Very important topic. The first property is linearity property. The basic thing is anything which conforms to two things. That means if it contains, if it is if any function, if it specifies the principle of superposition and also the principle of homogeneity, if it follows both, it calls a linear function. Okay, then linearity property of the Laplace transform says that if I have two signals, if x1t has got the Laplace transform x1s with ROC as R1 and x2t has got Laplace transform as x2s with ROC as R2, then ax1t plus bx2t has got the Laplace transform A x1s plus B x2s with ROC as R1 intersection R2. Okay, this property is followed until there is no pole zero cancellation. But in case if pole zero cancellation takes place, then this property does not follow. Okay, we will see one example. Suppose x1s is 1 upon s plus 1 with real part of s greater than minus 1. x2s is 1 upon s plus 1 s plus 2 with real part of s greater than minus 2. Then if I then xs equals to x1s minus x2s, which is equal to 1 upon s plus 1 minus 1 upon s plus 1 into s plus 2, which is equals to 1 upon s plus 2, for which ROC is real part of s greater than minus 2. We can see that this is not the intersected ROC of two functions. We have seen that here pole zero cancellation has taken place, and due to that pole zero cancellation, ROC is not the intersected ROC, but it is a totally different ROC. So we have to be careful. Just write a note. If pole zero cancellation takes place, then ROC will be totally new rather than the intersected ROCs. This is a very important point, and it is to be taken care while finding the region of convergence when we add or subtract two different functions, two different Laplace transforms. Property number 2. This property is time shifting property. This is again an operation which we do on time. Suppose if xt has got ROC as Laplace transform xs with ROC equal to R, then x of t minus t naught is equal to, give me Laplace transform s t naught xs. ROC will remain unchanged. Remember, in this ROC will not change. And how to derive this? How we got this relation is, see the basic formula of x is equal to minus infinity to infinity x of t minus t naught e to the power minus st dt. Substitute t minus t naught equals to m. You'll get t equals to m plus t naught. dt equals to dm. Substitute it in the equation of Laplace transform. We'll have xs equal to minus infinity to infinity x of m e to the power minus s m plus t naught dt. I can write it like this: minus infinity to infinity x of m e to the power minus sm, sorry, I can write it like this, dm e to the power minus st naught. This is equal to x dash s equal to e to the power minus st naught x dash. In this way, a time shifting will change the Laplace transform by multiplication of e to the power minus st naught term. No change in region of convergence will take place. We have seen the shifting in time domain. Now there can be shifting in s domain also. The third property is shifting in s domain. Okay. Similarly, if xt gives me xs with the region of convergence equal to R, then x of s minus s naught will have effect on time domain signal as e to the power s naught t xt. Region of convergence will definitely change in this case, and the region of convergence is nothing but equal to R plus real part of s naught. That means ROC is also shifted by real part of s naught. Proof is similar to the above case. There we have shifted the s. In the previous case we have shifted the time. Here we have to shift it the s. Fourth property. We have seen the shifting in time domain. We have seen the shifting in s domain. Now there is another one called time scaling. Time scaling property. Okay, that means we are performing some operation on time again. If xt gives me access with ROC equal to R, then x of at will give me 1 upon mod a x of s by a. ROC will become R by a. That means we have seen that. Now we can conclude something from this. ROC will change whenever the s will change. That means whenever the function, whenever the variable s of the Laplace transform will change, it will make a change in the ROC also. But if the variable s is not changing, the ROC will also not change. To prove it again, we'll use the same expression. Of s by a, ROC will become R by a. That means we have seen that. Now we can conclude something from this. ROC will change whenever the s will change. That means whenever the function, whenever the variable s of the Laplace transform will change, it will make a change in the ROC also. But if the variable s is not changing, the ROC will also not change. To prove it again, we'll use the same expression. Substitute at equals to m, we'll get dt equals to dm by a. We'll get x dash s is equal to minus infinity to infinity x of m e to the power minus s by a t s by a m dm by a is equals to 1 upon a minus infinity to infinity x of m e to the power minus s by a m dm is equals to 1 upon a x of s by a. ROC will be r by a. Now in this only, if xt is equal gives me Laplace transform as xs, then x of minus t will give me Laplace transform of x of minus s. ROC will be minus r. Okay. Next property. Differentiation in time domain. If xt gives me xs as a Laplace transform, then dxt by dt will give me s into xs. If previously if ROC is equal to r, in this case also ROC will remain equal to r only. In case if any pole present at s equal to 0, then that will get cancelled and ROC will change accordingly. Okay.